Hi there, I'm Dr. McFerrin with DM Explains. In this video, I'm going to talk about complementary MOSFET circuits, which can be used to implement digital logic. So, a transistor at basic level can be viewed as a switch. So, a traditional MOSFET transistor, we can imagine as looking like this, where I've got a drain, a gate, and a source. And as long as the gate voltage is large enough to accomplish the turn on condition for the MOSFET, then let's say the gate is a digital 1, then I get a equivalent resistance, which I'll call R on, between the drain and the source, and current is allowed to pass. Usually we set V gate for the digital 1 to be equal to VDD, so it's a digital or logical high. When the gate is a logical 0, then it looks like an open switch, and so here the V gate is equal to 0. So this gate voltage controls the switch. So this example that I've given you is for an N-type or an NMOS transistor. On the other hand, I can use a PMOS. So if the gate is here and I've got my little arrow here, this is my source and my drain. Then if the gate is a logical 1, then the switch looks open. And if the gate is a logical 0, then the switch looks closed. And so they behave in a complementary fashion. If one input is going to make an N-type on, then it'll make a P-type off. And so typically we will package an N-type and P-type MOSFET together to get what's called CMOS, or complementary MOSFET. The C stands for complementary, meaning that the behavior of one is the opposite as the behavior of the other. Before I launch into showing you how we might construct logic circuits using these transistors, I want to give you some alternate circuit symbols just to make things a little cleaner. So for an NMOS, we're going to represent it with a transistor, no arrows, and then for a PMOS, we'll represent it by putting a bubble here right at the gate connection. And that bubble represents not. And so for a logic gate, if I have a little bubble, it represents not. So it's saying I've got an NMOS and not NMOS, not being the logical opposite. We probably should introduce De Morgan's law. If you've taken digital logic, this will be familiar to you, but it's worth going over if you haven't. It says that not A or B is equal to not A and not B, as well as not A and B is equal to not A or not B. So with that information in mind, let's look at the CMOS inverter. In the CMOS inverter, what I'm going to do is I'm going to get an output Y, and that output is just not X. So if I were to draw that in a digital electronics way, I would use a NOT gate. So X is the input, and Y is equal to not X. So if I draw this exact thing using my transistors, I'll have VDD, and then I will have a PMOS transistor up here, and then I'll also have an NMOS transistor down here. That's ground. These are connected together to X, and the output is measured between them. That's Y. So let's see how this thing, let's sort of encircle this or box this so we know that that is what it looks like. But how does this operate? Well, if X is equal to 1, let's go back up to our conditions here. For a PMOS, if the value is 1, a logical 1, it looks open. So if X is equal to 1, I've got VDD, I've got a nice open here. And I know that the output is measured between them. And if X is equal to 1, I also know that the NMOS acts complementary to the PMOS. And so that looks like a little resistor here with ground. And so what happens is that if X is equal to 1, the value of Y is equal to 0 because this resistor serves as a pull down. On the other hand, if X is equal to 0, I'll get the opposite relationship where I have my PMOS as on and my NMOS as an open or off. And so if X is equal to 0, Y is equal to 1. So what's happening is that whatever X is, Y is the opposite. So that checks out logically. The general structure of any CMOS circuit is that I've got VDD, my source, and then I've got what's called a pull-up network, or a pun. There's nothing at all funny about that. And into this, I've got a bunch of inputs, let's say A, B, and C. And then I'll have the output Y measured right below the pull-up network, and below that I'll also have a pull-down network, or PDN, and then ground. And I also have the same inputs A, B, and C. So that is the general structure of a CMOS circuit. Let's look at what some common logic operations are when implemented using CMOS. So let's start with a NOR gate. A NOR gate, first of all, is represented by taking two inputs, A and B, and I have an OR, and then I put a bubble here to represent not OR. So Y is equal to A or B knotted or negated, which through De Morgan's law is the same as not A and not B. The truth table for this can be drawn. So let's say I've got A, B, A or B, not A or B. And then notably I'll also add not A, not B, and not A and not B. Since I am operating with two input variables, it means that I've got 2 to the n possible options. So to represent that, A could take 2 possible values, B could take 2 possible values, and the number of possible relationships are that there are 4 of them. A or B is the time at which either A is true or B is true. So in the first row, A and B are both 0. In the next one, A is true but B is not, but at least one of them is true. Same story going down, and then in the last condition, A and B are both true. So not A or B is looking at this column here and then just replacing all the zeros with ones and all the ones with zeros. So this becomes 1, 0, 0, 0. So this is the actual thing that I am trying to implement using my CMOS. Just to verify De Morgan's law does in fact work. Not A is just the opposite of A, and not B is just the opposite of B, and not A and not B is the case when both not A is true and not B is true. That only happens in the first row. So these are actually the exact same realization. Now, let me give you the circuit and we'll talk about it a little bit. Here's VDD. The pull-up network is implemented using the PMOS. So I've got A and B here. Y is measured at the output. And then I have in parallel in the bottom 2 NMOS. So in series things are ANDed, and in parallel things are ORed. So let's evaluate this in the different cases and then we'll move on to the next option. So if A is equal to 0 and B is equal to 0, what that means is that the transistor related to input A is on, the transistor related to input B is on in the PMOS pull-up network, and they're off in the bottom. And so the result is Y is equal to 1. What happens in all of the other cases is if either A or B are 1, then this looks open. And because they're in series, it has to pass through both of those transistors. They both have to be on. On the other hand, as long as one of them are 1, the NMOS transistors will look like they're on, and there's a resistance there which pulls Y down to 0. So all other cases, Y is equal to 0. So that is a NOR gate. Next, let's talk about a NAND gate. If you aren't familiar with what a NAND gate is, it is an AND gate, A and B, but it's knotted or inverted to get Y. So in equation form, Y is equal to A and B knotted, which through De Morgan's law is not A or not B. The truth table for this, A, B, A and B, not A and B, not A, not B, not A, or not B. So A, let's go 0, 1, 0, 1, B, 0, 0, 1, 1. A and B is the case when both A and B are true, so that's 0, 0, 0, 1. So the knot of that would be 1, 1, 1, 0. For completeness, let's fill out the not A and not B, and I just need an OR between these, so it should be 1, 1, 1, 0. All right, so the way that this will look is that in the pull-up network, I'm going to have a parallel combination of PMOS transistors for A and B, and in the pull-down network, I'm going to have a series combination of NMOS transistors for A and B. And you can check that on your own to see that that does in fact meet the requirements. One more basic version of a circuit to do before we talk about how we might synthesize our own CMOS networks. And that example is an XOR, or an exclusive OR. Exclusive OR says either A is true or B is true, but not both. The equation form of that is that Y is equal to A and not B, or not A and B. It is potentially useful to write not Y. Not Y is A and B, or not A and not B. I'm not going to write the truth table here, but I'm going to highlight sort of how we're going to move from here to a synthesis method. So one thing we could do is we could start with the pull down network here. And if I look at the not Y expression, it turns out that I'm going to get A and B, so in series, in parallel with not A and not B. I've got not Y is A and B, or not A and not B. That turns out to be exactly the pull down network. Then what I'll do is I'll go up to the pull up network, and I'll have in parallel not A in series with B is in parallel with A in series with not B. So we're starting to potentially see a pattern of how we might be able to do this. But that's my circuit. So what is the synthesis method? I'm going to change colors just to highlight this. Here's my synthesis method. I've got sort of some options. The first option is that the pull down network is most directly synthesized by expressing Y naught as a function of uncomplemented variables. And what I mean by that is that I'm just going to figure out what not Y is, or Y naught, and then I'm just going to represent it straight up based on what I found Y naught to be, just like I did in the previous example. Note, if any variables are complemented, then the real circuit would include an inverter. All right, that's a little side note. Number 2, if I don't like the option of finding why not and then implementing that, I can use the PUN, pull-up network, and I could just write y as a function of complemented variables. We'll see what that means here in a moment. And then 3, whether I pick 1 or 2, we get the pull-down network from the pull-up network, or pull-up network from the pull-down network, using what's called the duality property. All that is that series in one network is converted to parallel in the other. Why don't we actually look at this in some detail? Let's look at an example that says synthesize a CMOS logic circuit that implements y is equal to A or B and C or D knotted. So when I look at this, it's very easy to get not y. Not y is just A or B and C or D. So all I've got to do then is implement my pull-down network. So if I implement this pull-down network, an OR is represented by parallel. So let's say I'm doing my pull-down network here. So A, or this part on the right-hand side here, is implemented using parallel. So this is A. And then B and C or D. C or D is implemented in parallel, and B should be in series with that. B is in series with the parallel connection of C or D. And that's my pull-down network. To get the pull-up network, let's use duality. And so the parallel combination of A with this stuff, it becomes a series combination. So let's assume I've got Y here. Let's put A in series with the other stuff. And I'm using a PMOS. And then B should be in parallel with the series combination of C and D. And I'm done. If I put the pull-up and pull-down network together, I will have my whole CMOS network. So if I go down and look at another example here, let's find Y equal to not A and B or C and D in terms of complemented variables. So using De Morgan's law, I know that Y is equal to, let's start with the base, not A and B or C, D. The law says that if I have two variables that are ANDed together and I knot them, that's equal to the OR of each one individually. So Y is equal to not A or not B and or C and D. And then we can look in here. I've got an OR, and this is knotted. So this is Y is A or not B and not C and D. So those are lumped together. And then I can take this part here, and I get Y is equal to not A or not B ANDed with not C or not D. Okay, I would like to do two more examples of CMOS synthesis, and then I'd like to end the lecture. So example number 3 says synthesize the CMOS logic circuit for Y is equal to A and B or C. So I have two real options here. I could start with the pull up network or start with the pull down network. I think that probably it's easiest to start with the pull up network, and what I want to do is I want to represent Y as is but complement each variable. That's what the rule for pull up network is. So if I've got A and B, I'll draw A and B, they're in series, except that I'm going to replace A with not A and replace B with not B. And ORed with C means that's in parallel. So that's ORed with not C. Then if I go to the pull down network, I'll use duality. So I know that C needs to be in series with the parallel combination of A and B. All of these are knotted variables. We're going to use the same inverted variables that I had above. So not A is in parallel with not B. And I'm done. I have my synthesized circuit. Okay, one more example. Example number 4, I believe. And this one says, let's synthesize a CMOS logic circuit that implements Y is equal to A or B and C or D knotted. So now I again have a choice. Do I take the pull down network first or the pull up network first? It turns out that the pull down network might be easier. I can write not Y just by knotting the other side. That's just A or B and C or D. And so the pull down network is just the representation of that. So let's start with the pull down network. I'll leave space for the pull up network above. So A or B. So A or B is a parallel combination. A or B. And then those are in series with a parallel combination of C or D. And to get the pull-up network, all I'm going to do is use duality. So A should be in series with B, and C should be in series with D, and those two things should be in parallel. So I've got A in series with B, in parallel with C in series with D. All right, that is the conclusion of that example and the conclusion of my lecture on CMOS and implementing logic circuits using transistors. In a digital logic course, you wouldn't think about the transistors. You look at the gate level like NAND and NOR gates and XOR gates and so on. But in this case, all I'm doing is using transistors to implement that. That's all I have for now. Thanks for watching. The result is Y is equal to 0. Nope. Too many lines here. Too many lines. Too many lines. Nope. Oops. And I'm done. Parts.